So the average undergrad I encounter was a lot better than their peers at math when they were in high school. And yet with nearly 100% probability, their preparation to do any sort of trigonometry is abysmal. Something that universal is clearly not your fault. It's not like you have control over your education system. I've been working on an in-depth trigonometry course with assignments, which will hopefully garner some interest. But in the meantime, I thought I'd record a little crash course lecture with no assignments. Hopefully some of you guys will watch it and find yourselves better prepared. So we start with a unit circle, where by unit we mean that the radius is 1, centered on the origin. We can pick a random point on this circle. Now, because we're restricting the point to being on the circle, this is a one-dimensional setup. You can see that because you can specify its location with just one number. If we look at where the circle intersects the positive x-axis and measure the distance counterclockwise from there, we get a number we can call theta. And that will completely specify the exact point we chose. Now, we can more naively specify its coordinates x and y in 2 dimensions, taking no advantage of the fact that it's confined to the unit circle. And now we run into a problem, or at least a question. Theta completely determines the location of the point, and so do x and y. So if we know theta, we should be able to calculate x and y. And this is absolutely true, but it turns out that we would need some transcendental functions. So what we can do is just define 2 transcendental functions of theta, one of which gives you the x-coordinate of the point, and one of which gives you the y-coordinate of the point. Hopefully these look familiar. Now obviously, if we want to, we can draw a radius out to this point. What's the length of this radius? Well, it's a unit circle, so by definition it's 1. We can also make projections of this radius, and since we know the point's coordinates, we know the lengths of these projections. And now, you can use the Pythagorean theorem to quickly get an identity. Okay, and just a quick review of secant lines and tangent lines. You guys don't appear to learn any Greek or Latin by the time you get to college. Again, not your fault. It's how you're taught, but it puts you way behind on a lot of technical terminology. But you've probably at least seen the root of the word secant in words like section, dissect, intersect, etc. It means to cut. And a secant line cuts through a curve, i.e. it crosses through it. You may have seen the root from the word tangent most directly in the word tangible. The other words where it appears in English tend to be a bit harder to connect to it. It means to touch, and a tangent line touches a curve without crossing through it. You'll notice that the x and y coordinates are secant lines to the circle. And we don't really see any tangent lines, so let's draw one through our point. We can label its x-intercept like this, naming it this way because it's a distance along the x-axis, which is a secant. And since we've used up that name for the x-intercept, we can label the y-intercept like so, to stay consistent with the prefix co for our complements. On the tangent line itself, let's call this segment the tangent of theta. So now we'll have to call this other segment the cotangent. Now, the radius and the tangent line form a right angle. You can prove that by symmetry. So you'll notice that the tangent of theta forms the leg of a right triangle. And we can use the Pythagorean theorem to generate another identity. And you may observe that this right triangle is similar to the one formed by the sine of theta and the cosine of theta. So you can set some ratios equal to get another identity. I encourage you to put some effort into making sure that these identities are accurate, and then coming up with some of your own involving the cotangent, some of your own involving the secant, the cosecant. Now let's talk about scaling, since not everything in life happens on a unit circle. Suppose you have a right triangle with hypotenuse r. Now given an angle theta, if the hypotenuse had been 1, the legs would just be sine of theta and cosine of theta like we did on the previous board. But since we're just scaling the hypotenuse by a factor of r, We can do the same with the legs. And now, observe the obvious. Sine of theta is the length of the opposite leg over that of the hypotenuse. You probably memorized this as the definition of the sine. It's weak, very weak and insufficient as a definition. Just try using it for an obtuse angle. But it will certainly serve you well as a property of the sine. Same, obviously, for the cosine. Now, on the previous board, we already derived that the tangent is the ratio of the sine and the cosine. And if we throw some r's in, we get your memorized high school definition of the opposite over adjacent. Okay, before I finish, I want to do a quick overview of the most basic angle addition formulae, since I noticed that many of you guys see them as these really long and confusing things you tried to memorize but quickly forgot. To get the angle alpha plus beta, I just put them next to each other like so. And I can tweak the lengths of the line segments I use so that I can connect their ends to make a right angle. I can also scale them so that this one has a length of 1. And then I can put a rectangle around them. Now it's totally basic to get the lengths of the legs of the inner triangle. And since we just talked about scaling on the previous board, we can just as easily get the lengths of the legs of the triangle at the bottom. With just a teeny bit of geometry, we can show that this angle is also alpha. And now, perhaps turning our head 90 degrees, we can get the lengths of that triangle, the legs of that triangle. Now, the top and bottom of the rectangle, are parallel to each other. So this angle is just also alpha plus beta. And now, perhaps hanging upside down, we can get the lengths of the sides of the triangle on the left. And just knowing that the opposite sides of a rectangle are the same length, we get these angle addition formulae. You will particularly commonly see them as double angle formulae where you're adding two of the same angle. Just substitute theta for both alpha and beta to get those. Now, there are obviously tangent addition formulae, and there are a whole lot more to do with trigonometry, but you'll learn it better if you try it for yourself, and this ought to get you guys started.